February 23rd, 1942. Swanage, Dorset. The household scissors trembled slightly in Joan Curran's hand as she cut through the thin aluminum foil spread across her kitchen table. "This cannot work," her husband Sam had said just an hour earlier, watching her transform rolls of ordinary metallic paper into what appeared to be nothing more than confetti. No enemy radar system could be fooled by something this simple. Through the cottage windows, she could see the grey waters of the English Channel, and beyond that invisible horizon, the German-occupied coast of France. Somewhere across those waters, Würzburg radar stations tracked every Allied aircraft that dared approach continental Europe. Their precision was devastating. Their effectiveness was bleeding RAF Bomber Command dry. 73 bombers lost in a single raid on Nuremberg. 88 lost attacking Berlin. Young men burning alive in Lancaster fuselages because German radar could see them through darkness, through clouds, through the meteorological protection that had once kept bombers safe. Yet here, on Joan Curran's kitchen table, lay what she believed could render those sophisticated radar systems completely blind. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Strips of aluminum foil, 1.5 centimeters wide, 25 centimeters long, cut with household scissors and bundled into 1-pound packets. The idea was so simple that senior RAF commanders had dismissed it as wishful thinking when she first proposed it 18 months earlier. What neither Curran nor her colleagues yet fully understood was that these crude metallic strips would soon transform the air war over Europe more decisively than any new bomber, any new weapon, and any tactical innovation yet deployed. The mathematical certainty of Allied victory was being written not in bombing strategy or fighter tactics, but in the electromagnetic principles that would make 10,000 ghost aircraft appear simultaneously on German radar screens. The psychological transformation had begun months earlier, not in British laboratories, but in German skies. Throughout 1941 and into 1942, RAF Bomber Command had watched its losses climb to unsustainable levels during night raids over Germany. The Germans had perfected something the British barely understood: a comprehensive radar-directed defense system that could track bombers through complete darkness with terrifying precision. On the night of November 30th through December 1st, 1941, RAF Bomber Command dispatched 131 aircraft to attack Hamburg. The German defences, guided by Würzburg fire control radar and Freya early warning systems, destroyed 23 bombers, a 17.5% loss rate. Statistically, this meant bomber crews had almost no chance of surviving their required 30-mission operational tour. The mathematics were inescapable and brutal. If losses continued at 15 to 20% per mission, the average crew would be shot down by their 7th or 8th sortie. Young men, 22 and 23 years old, calculated their survival odds during briefings, seeing death not as a possibility, but as a statistical certainty approaching with each mission. Air Chief Marshal Arthur Harris, appointed Commander-in-Chief of RAF Bomber Command in February 1942, confronted this grim arithmetic daily. His office maintained detailed plots of every raid, every target, every loss. The patterns emerging from these statistics made strategic bombing appear impossible according to conventional calculations. German radar-directed defences were simply too effective. Würzburg radar, the primary German gun-laying system, could track individual aircraft with angular accuracy of 0.1 to 0.2 degrees. This precision, combined with radar-predicted firing solutions fed directly to anti-aircraft batteries, created a lethal defensive network. Flak guns no longer fired blindly into the night sky, hoping for lucky hits. They fired at specific coordinates where radar predicted the bomber would be 3 seconds later when the shells reached altitude. The system's effectiveness was documented in chilling detail by RAF intelligence analysts. German night fighters, guided to interception points by Freya early warning radar, and then directed onto precise attack vectors by ground controllers watching Würzburg displays, achieved kill rates approaching 30% once they located bomber streams. A single German fighter pilot with radar assistance could destroy 2 or 3 British bombers in one night, returning to base with ammunition remaining. Harris convened crisis meetings throughout March and April of 1942 with Britain's top scientists and radar experts. The discussions revealed both sophisticated understanding of the German systems and frustrating inability to counter them effectively. British scientists knew precisely how Würzburg functioned. They understood its 50 to 60 centimetre operating wavelength. They had calculated its maximum range of approximately 40 kilometres and its minimum range of roughly 500 metres. This knowledge came from extraordinary intelligence gathering. In February 1942, British paratroopers had conducted Operation Biting, a commando raid on a German Würzburg installation near Bruneval on the French coast. Flight Sergeant C.W.H. Cox, an RAF radar specialist, had accompanied the raid specifically to dismantle and photograph the system's critical components. Under fire from German defenders, Cox had systematically dismantled the Würzburg's receiver assembly, photographed the antenna feed mechanism, and sketched the display systems before the raiders withdrew. The captured components, along with a German radar technician taken prisoner during the raid, allowed British scientists to understand exactly how effective German radar had become. The Bruneval Würzburg used a 3-metre parabolic dish antenna with a conical scanning system that spun at 25 cycles per second. This spinning feed, called a quirl by the Germans, provided remarkable tracking accuracy by detecting slight variations in signal strength as the beam swept across the target. More critically, the Germans had deployed thousands of these systems across occupied Europe. Intelligence estimates suggested over 4,000 Würzburg radars of various models were operational by early 1942, forming an integrated defensive network that covered every likely bomber approach route into Germany. Each Würzburg was linked to multiple anti-aircraft batteries or assigned to guide night fighters, creating overlapping defensive zones that bombers could not avoid. Freya early warning radars, operating at longer wavelengths around 2.4 meters, provided the outer detection layer. These systems could detect bomber formations at ranges exceeding 100 kilometers, giving German defenders nearly an hour's warning before raids reached their targets. The Freya radars would track the general direction and approximate altitude of incoming formations, then hand off precise target information to the shorter range but more accurate Würzburg systems as bombers came within range. The integrated nature of this defensive network represented something new in warfare, the systematic application of electronic technology to air defense on a national scale. German commanders called it the Kammhuber Line, named after General Josef Kammhuber, who had organized the system. The line divided German airspace into sectors, each covered by dedicated radar systems, night fighter squadrons, and anti-aircraft batteries, all coordinated through central control rooms. British attempts to counter this system had achieved only marginal success. Electronic jamming, codenamed Mandrel, could temporarily blind Freya radars by transmitting powerful noise on their operating frequencies. But the Germans simply switched to alternate frequencies or increased transmitter power. Bombing raids targeted suspected radar factories, but German industry proved capable of rapidly replacing destroyed equipment. Tactical adaptations provided no solution. Flying lower made bombers vulnerable to lighter anti-aircraft guns and increased fuel consumption. Flying higher simply gave radar more time to track and engage. Varying approach routes meant abandoning the direct paths that minimized time over defended territory. Concentrated bomber streams overwhelmed individual German defensive sectors, but created massive, easily tracked formations that radar could detect from extraordinary distances. The fundamental problem was electromagnetic. Radar operates by transmitting radio waves and detecting the reflections that bounce back from objects. Aircraft, with their large metal surfaces, provide strong radar returns that can be detected at great distances. As long as bombers were made of aluminum and steel, they would remain visible to radar, regardless of tactical maneuvers or defensive equipment. This was the problem that Joan Curran had been studying since late 1940 through her work at the Telecommunications Research Establishment near Swanage. Curran, born Joan Struthers in Wales in 1916, had studied physics at Cambridge University's Newnham College on a full scholarship. Although she completed honours degree requirements in 1937, Cambridge still did not award actual degrees to women, a policy that would not change until 1948. After her undergraduate work, Curran had won a government grant to pursue doctoral research at Cambridge's Cavendish Laboratory, one of Britain's most prestigious physics research centres. There she worked with Samuel Curran, a fellow physicist with whom she would eventually marry in November 1940. But the war intervened before either could complete their doctoral studies. By September 1939, both had been recruited into Britain's secret radar research programme. The couple was initially assigned to the Royal Aircraft Establishment at Farnborough, then quickly transferred to the physics department at the University of Exeter, where they worked on proximity fuses, devices that would detonate anti-aircraft shells automatically when they came close to enemy aircraft. This work gave Curran deep familiarity with radio frequency technology and electromagnetic wave propagation, the fundamental principles that would inform her most important contribution to the war effort. In late 1940, both Currans were transferred again to the Telecommunications Research Establishment, Britain's central facility for radar development and countermeasures research. Sam Curran worked on centimetric radar, helping develop the revolutionary cavity magnetron technology that would give Britain decisive advantages in radar sensitivity. Joan Curran was assigned to the countermeasures group in an adjoining laboratory, tasked with finding ways to defeat German radar systems. This assignment led Curran to consider a principle that radar experts had understood theoretically for years, but never successfully weaponized: that small reflective objects cut to specific dimensions could generate radar returns, mimicking much larger targets. The physics were straightforward. When electromagnetic radiation encounters a conductive surface with dimensions close to half the radar's wavelength, the surface acts as a resonant antenna, reflecting the radiation back toward the source with surprising efficiency. For Würzburg radar operating at wavelengths around 50 to 60 centimeters, optimal reflectors would measure 25 to 30 centimeters long. For Freya radar at wavelengths around 2.4 meters, reflectors would need to be roughly 1.2 meters long. If large, numbers of these precisely sized reflectors could be distributed in the air. They would create multiple radar returns that could potentially obscure or confuse the actual bomber targets. The concept was not new. British scientists had discussed radar deception techniques as early as 1937, shortly after radar itself was developed. German scientists had independently reached similar conclusions and developed their own experimental chaff, which they called Düppel, after the Berlin suburb, where early tests occurred. Both sides understood the theoretical possibility of radar jamming through reflective strips. What prevented deployment was mutual fear. British military leadership worried that if RAF bombers used chaff to blind German radar, the Germans would immediately copy the technique and use it against Britain's own radar network. Britain's air defence during the Battle of Britain in 1940 had depended entirely on chain-home radar stations detecting incoming German bomber formations. If the Germans deployed chaff, Britain's early warning system would become useless. Professor Frederick Lindemann, Winston Churchill's chief scientific advisor, had argued strenuously against deploying any radar countermeasure that enemies could easily copy. In a memo circulated in April 1942, Lindemann warned that the temporary advantage gained from blinding German radar would be vastly outweighed by the permanent disadvantage of teaching the enemy how to blind our own defensive systems. This cautious thinking frustrated RAF Bomber Command's operational planners who watched loss rates climb while a potentially life-saving countermeasure sat unused. Air Marshal Arthur Harris, never one to accept bureaucratic inertia passively, began pressing for reconsideration of the Chuff decision in mid-1942. His argument was pragmatic rather than technical. By mid-1942, the Luftwaffe was conducting relatively few bombing raids against Britain, having transferred most bomber squadrons to the Eastern Front, where they supported operations against the Soviet Union. Germany no longer possessed the bomber force necessary to threaten Britain seriously, Harris argued, making British radar less critical to national survival. Meanwhile, RAF Bomber Command was sending hundreds of aircraft over Germany nightly, suffering catastrophic losses that would make strategic bombing completely unsustainable within months if nothing changed. The risk-benefit calculation had shifted decisively. Harris also pointed out that the expanding American bomber forces would soon join Bomber Command's campaign, multiplying the number of Allied aircraft over Germany. The combined bomber offensive, with American daylight raids and British night attacks, would saturate German defences through sheer numbers, making individual aircraft losses acceptable as long as enough bombers survived to reach targets. But only if those bombers had some way to degrade German radar effectiveness. The debate extended into the highest levels of British government. The War Cabinet reviewed the issue repeatedly throughout 1942, weighing Harris's operational arguments against Lindemann's strategic concerns. Intelligence assessments suggested that even if Germany copied British chaff techniques, German industry might require months to manufacture and deploy sufficient quantities to threaten British radar networks. Those months might be enough to alter the air war's trajectory. By early 1943, the balance of arguments had shifted. Germany was fully committed to fighting in Russia and the Mediterranean, leaving minimal bomber assets available for attacks on Britain. RAF Bomber Command's losses continued at rates approaching 20% on some raids, far above the 5% maximum considered sustainable for maintaining operational capability. The mathematics demanded action. Meanwhile, Joan Curran had been perfecting the technical details of what would become known as Window, the British codename for radar chaff. Her earliest experiments in late 1941 had tested various radar reflector designs. She tried single wires suspended from small parachutes, creating drifting reflective curtains in the sky. These produced radar returns but fell too slowly, creating stationary false targets that German operators quickly learned to ignore. She experimented with metal sheets the size of notebook paper, thinking they might serve dual purposes as propaganda leaflets with messages printed on one side. The sheets reflected radar effectively, but their large surface area made them too heavy, causing them to tumble unpredictably rather than descending steadily. They also tended to stick together in bundles rather than dispersing into clouds as intended. Through systematic trial and error, Curran refined the design during 1942. The optimal configuration emerged. Strips of paper coated on one side with aluminum foil, precisely 25 centimeters long and 1 to 2 centimeters wide. These strips were just long enough to resonate with Würzburg's operating wavelength, while narrow enough to flutter and disperse properly during descent. The aluminum coating provided sufficient reflectivity without adding excessive weight. The strips needed to be bundled carefully, too few per bundle, and they would disperse too quickly, creating brief flashes on radar that operators might recognize as false targets. Too many per bundle, and they would fall as a clump, again creating suspicious radar signatures. Curran determined that 1-pound bundles containing approximately 2,000 strips provided optimal performance. When dropped from bomber altitudes around 18,000 feet, the bundles would break apart gradually, creating a cloud of drifting reflectors that persisted for up to 15 minutes. The mathematics of deployment were equally critical. A bomber dropping one bundle every minute would leave a trail of chaff clouds along its flight path, each cloud creating multiple false targets on German radar screens. A formation of several hundred bombers, all dropping chaff simultaneously, would generate thousands upon thousands of phantom aircraft returns, completely overwhelming radar displays designed to track dozens of real targets. Curran arranged field tests in early 1942, using RAF aircraft operating from Christchurch Aerodrome near the Telecommunications Research Establishment. She coordinated with ground-based radar stations to monitor the effects as test aircraft dropped experimental chaff bundles. The results exceeded expectations. British radar operators watching their screens saw what appeared to be entire bomber formations where only single aircraft flew, exactly as Curran had predicted. Her husband Sam Curran later recalled watching one of these early tests with amazement. When the aluminum strips were dropped, the radar screens lit up with returns suggesting a large fleet of aircraft where none existed. The demonstration proved that the concept worked, at least against British radar systems that were technologically similar to German equipment. But proof-of-concept tests in controlled conditions differed vastly from operational deployment over enemy territory. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Numerous practical questions remained unanswered. Would the chaff survive the buffeting of actual bomb runs? Would static electricity cause strips to clump together, reducing effectiveness? Would German operators immediately recognize the false returns and develop countermeasures? Most critically, would the benefits justify giving Germany access to a technique that could potentially be used against Allied radar networks? The debate continued through spring 1943, while RAF Bomber Command's losses mounted. On March 5th through 6th, 422 aircraft attacked Essen. 14 bombers were lost. March 8th through 9th, Nuremberg. 435 aircraft dispatched, 19 lost. March 22nd through 23rd, Saint-Nazaire. 357 aircraft, 5 lost. March 26th through 27th, Duisburg. 455 aircraft, 9 lost. Each loss represented 7 trained crew members killed or captured, men who had completed months of expensive training and could not easily be replaced. Each loss represented 1 heavy bomber destroyed, aircraft that British factories were producing at rates that barely kept pace with attrition. The arithmetic of the air campaign was becoming impossible. On July 15, 1943, Winston Churchill personally authorized the operational use of window. The decision came after intensive review of the latest intelligence assessments, which confirmed that German bomber forces remained concentrated on the Eastern Front, with minimal capacity for major raids against Britain. Harris was authorized to deploy window on an operation of his choosing, allowing the technique to be evaluated under actual combat conditions. Harris chose Operation Gomorrah, a massive sustained bombing campaign against Hamburg scheduled to begin July 24, 1943. Hamburg was Germany's second-largest city, a major port and industrial centre containing vital shipyards, U-boat construction pens, and oil refineries critical to the German war effort. The city had been attacked numerous times before, making it heavily defended with extensive radar coverage and substantial anti-aircraft batteries. Hamburg represented an ideal test case for window. If the chaff could degrade German defences enough to reduce losses during raids on such a heavily defended target, it would prove effective against any German city. If window failed to provide sufficient protection in Hamburg, the entire concept would need to be reconsidered before risking wider deployment. The operational planning for Gomorrah reflected window's experimental status. Only selected bomber crews received initial briefings on the new countermeasure. Security protocols prohibited mentioning window by name in any written orders that might be captured. Crews were instructed to refer to it simply as special equipment and told to drop 1 bundle per minute through the bomber's flare chute using stopwatches for precise timing. Production of window bundles became a massive industrial effort in the weeks before Gomorrah. Several British factories, working under Ministry of Aircraft production contracts, manufactured millions of aluminum-coated paper strips. Workers, many of them women in war production jobs, cut and bundled the strips by hand in the early production runs. As demand grew, more automated cutting and packaging processes were developed, but the scale remained enormous. Each bomber would carry dozens of bundles, and hundreds of bombers would participate in the initial raid. The strips themselves were manufactured from standard paper stock, approximately 0.02 mm thick, coated on one side with aluminum foil, roughly 0.003 mm thick. The aluminum had to be applied uniformly to ensure consistent radar reflectivity, but not so thickly that it added excessive weight. Quality control was critical. Strips that were too thick would fall too fast. Strips that were too thin might tear apart in the airstream, reducing effectiveness. Each bundle was wrapped in paper and tied with cord that would break easily when the bundle was dropped, allowing the strips to disperse properly. The bundles weighed approximately 1 pound, as Curran had specified, making them light enough to drop easily through bomber flare chutes, but heavy enough to fall clear of the aircraft before dispersing. Incorrectly weighted bundles might disperse prematurely, covering the dropping bomber itself with chaff and potentially interfering with its own radar systems. As production accelerated through July 1943, British factories produced over 2,400 bundles for the initial Hamburg raid, enough to equip 791 bombers with multiple bundles each. The total amount of aluminum-coated paper exceeded 40 tons, representing a significant allocation of materials in a nation where every resource was carefully rationed for maximum war production efficiency. While factories prepared the chaff, RAF Bomber Command finalized operational details for Gomorrah. The raid would actually consist of multiple attacks spread over several nights, combining British nighttime raids with American daylight strikes to maintain constant pressure on Hamburg's defenders and prevent effective damage repair between attacks. The opening night raid on July 24th through 25th would be the largest, incorporating Window's combat debut. Supporting the bombers would be Pathfinder Force, aircraft, specialized squadrons trained in precision navigation and target marking. These aircraft would arrive first, identifying the target area using H2S ground mapping radar, another recent British innovation. The Pathfinders would drop colored marker flares, creating visual aiming points for following bomber waves. This technique had proven effective in concentrating bombing patterns, creating devastating fire damage in targeted urban areas. The combination of Pathfinder marking, heavy bomber concentration, and window countermeasures represented the culmination of 3 years of tactical and technological development in strategic bombing. If the operation succeeded, it would validate both the massive investment in bomber production and the strategic bombing doctrine that Harris had championed since taking command in early 1942. But none of this sophisticated planning would matter if German radar-directed defences could continue shooting down bombers at rates approaching 20% per mission. Everything depended on Joan Curran's household scissors, her kitchen table experiments with aluminum foil, and the fundamental electromagnetic principles she had translated into bundles of metallic confetti now loaded into hundreds of bombers waiting on airfields across eastern England. On the afternoon of July 24, 1943, bomber crews attended final mission briefings, where they learned they would be using special equipment to confuse German radar. Many crews were skeptical. The idea that strips of paper could blind sophisticated radar systems seemed like wishful thinking, another one of the boffin's impractical theories that would probably get them killed when it failed to work as promised. But orders were orders. At approximately 21:45 hours, the first bombers began taking off from their bases. Heavy Lancaster bombers, Halifax bombers, and Sterling bombers, each loaded with thousands of pounds of high, explosive and incendiary bombs, and each carrying something new, dozens of 1-pound bundles of aluminum-coated paper strips that would, within the hour, transform the nature of electronic warfare forever. 23 minutes past midnight, July 25, 1943, Würzburg Radar Station, Hamburg-Harburg Defensive Sector. Obergefreiter Hans Richter sat at his display console, tracking the familiar pattern of approaching British bombers across the North Sea. His screen showed approximately 60 distinct aircraft returns at ranges between 70 and 90 kilometers, their positions updating every few seconds as the Würzburg's rotating antenna completed each sweep. This was routine. Richter had tracked hundreds of RAF raids during his 14 months operating Würzburg systems. The procedure was standardized. As bombers entered his sector, he would measure their precise range, bearing, and elevation, feeding this data through telephone lines to the fire control center that directed 4 batteries of 88mm anti-aircraft guns. The system had proven devastatingly effective, destroying dozens of British bombers in previous raids. Then, at 0:27 hours, something impossible appeared on his screen. Within 30 seconds, the 60 distinct aircraft returns multiplied into several hundred. then thousands. His display, designed to track perhaps 40 or 50 individual targets, became a solid mass of returns. Every sweep of the antenna added more false echoes. The entire screen turned white with overlapping target indicators. Richter checked his equipment, convinced the Würzburg had suffered catastrophic malfunction, but the system's self-test indicators showed normal operation. Transmitter power was stable, receiver sensitivity was within specifications. Antenna rotation was smooth and constant. The equipment was functioning perfectly, while displaying a physical impossibility. On the ground below his radar station, searchlight batteries that depended on Würzburg guidance swept aimlessly across the sky, unable to acquire specific targets from the mass of confusing returns. Anti-aircraft batteries fired blindly at approximate altitudes, their radar-directed fire control systems completely overwhelmed. Night fighters scrambled to intercept the raid found themselves receiving contradictory vectors from ground controllers who could no longer distinguish real bombers from phantom returns. What Richter witnessed in that moment represented the greatest single disruption of radar operations in military history. Across the entire Hamburg defensive network, every Würzburg and Freya radar station was simultaneously experiencing identical catastrophic degradation of performance. The sophisticated integrated defense system that had cost Britain hundreds of bombers in previous raids had become effectively blind in less than 1 minute. 3,000 meters above Richter's radar station, flying Officer James Morton piloted Lancaster bomber EE-139 through the night sky. Every 60 seconds, his flight engineer dropped one bundle of window through the flare chute, watching it tumble away into the darkness. Morton had no idea whether the aluminum strips were having any effect. From his perspective, the mission seemed no different from dozens of previous raids over Germany, except for one critical difference. The usual curtain of searchlights that typically illuminated bomber streams as they approached Hamburg was absent tonight. Individual searchlights stabbed upward randomly, but failed to achieve the concentrated cones of light that normally trapped bombers for anti-aircraft gun engagement. Flak explosions dotted the sky, but without the tight patterns that indicated radar-directed fire. Shells were detonating at incorrect altitudes, dozens or even hundreds of meters below the bomber stream. Morton realized something extraordinary was happening when his crew passed directly over known anti-aircraft battery positions without receiving accurate fire. During the March raid on Hamburg, this same approach vector had been a wall of precisely aimed explosions. Tonight, the flak was scattered and ineffective, bursting in random patterns that posed minimal threat to properly flown aircraft. 791 bombers participated in the initial Hamburg raid that night. Of these, 728 successfully dropped their bombs on the target, guided by Pathfinder marker flares that were clearly visible without the usual searchlight interference. The raid lasted approximately 50 minutes, during which time RAF bombers dropped over 2,300 tons of mixed high explosive and incendiary bombs into Hamburg's densely built working-class districts. The destruction was catastrophic for the city below. With fire services unable to respond effectively due to bomb damage and the sheer number of separate fires started simultaneously, flames spread through neighborhoods of closely packed wooden buildings. But from RAF Bomber Command's operational perspective, the most significant statistic was the loss rate. Only 12 aircraft were shot down during the raid. Out of 791 bombers dispatched, 12 lost represented a loss rate of 1.5%. For comparison, the March 5th through 6th Essen raid had suffered 3.3% losses. The March 22nd through 23rd St. Nazaire raid had lost 5.4%. Individual raids had experienced losses exceeding 10%, occasionally approaching 20% on particularly well-defended targets. Hamburg itself, attacked multiple times previously, had consistently inflicted losses around 4 to 6% on RAF bombers. The mathematics were stunning. If window reduced losses from an average of 5% to 1.5%, the impact on RAF operational capability was transformative. At 5% losses per mission, The average bomber crew would be shot down by their 14th mission. At one point, 5% losses, that survival probability extended to 46 missions, well beyond the 30-mission operational tour that crews were required to complete. This single technological innovation had effectively tripled bomber crew survival rates. For the young men flying these missions, men who had been calculating their own death probabilities before every briefing, window represented not just tactical advantage, but hope of actually surviving the war. The impact on German defenders was equally dramatic, but psychologically devastating in a different way. When the Hamburg raid ended and German radar operators were finally able to assess what had occurred, the realization spread rapidly through defensive command centers. The enemy had deployed a countermeasure that rendered Germany's sophisticated radar network almost useless. Years of engineering development, millions of Reichsmarks invested in radar production, thousands of trained operators, all defeated by paper strips coated with aluminum. General Major Josef Kammhuber, architect of Germany's integrated air defense system, received initial reports from Hamburg with disbelief that hardened into alarm as confirming reports arrived from other defensive sectors. The British had used some form of radar deception that created thousands of false targets simultaneously. Every radar station from the coast to Hamburg had been affected identically, suggesting this was not equipment malfunction but deliberate enemy action. Technical analysis teams rushed to Hamburg to investigate. They quickly identified the culprit. Strips of aluminum-coated paper found littering streets and rooftops throughout the city. Laboratory examination revealed the strips measured approximately 25 centimeters long, precisely half the wavelength of Würzburg radar operating frequencies. The design was elegant, economical, and devastatingly effective. German scientists immediately recognized what they were examining. This was Dupel, the chaff concept that German radar experts had developed but deliberately never deployed for fear of enemy retaliation. The British had apparently reached the same conclusions, overcome their own fears of retaliation, and deployed the countermeasure first. The irony was bitter. Germany possessed complete knowledge of how to manufacture and deploy identical countermeasures. German factories could produce chaff within weeks, but this knowledge provided no solution to the immediate crisis. German radar operators had no effective way to distinguish real aircraft from chaff clouds using existing equipment. The British had seized the tactical initiative, and German defences had no immediate counter. Emergency meetings convened in Berlin as senior Luftwaffe commanders grappled with the implications. Hermann Göring, Reichsmarschall, and Commander-in-Chief of Luftwaffe, reportedly exploded in fury when briefed on the Hamburg disaster. The sophisticated air defense network he had championed, the integrated system of radar and night fighters and anti-aircraft batteries, had been rendered obsolete by paper and aluminum foil. German engineers proposed immediate countermeasures. Radar systems could be modified to detect moving targets, while filtering out slowly drifting chaff clouds. This technique, based on Doppler frequency shifts created by moving aircraft, would theoretically allow radar to distinguish between bombers flying at 300 km per hour and chaff clouds drifting at wind speed. But implementing such modifications across thousands of radar sets would require months. Meanwhile, RAF Bomber Command had no intention of granting Germany months to adapt. Operation Gomorrah continued with follow-up raids on successive nights. July 25th through 26th saw American 8th Air Force B-17 bombers attacking Hamburg in daylight, targeting specific industrial facilities with precision bombing. The Americans did not use window during these daylight raids, as visual identification made radar less critical to their operations. But the night of July 27th through 28th brought the most devastating raid of the entire operation. 787 RAF bombers attacked Hamburg for the third time in 4 nights, again employing window to blind German radar defences. This raid, combined with unusual weather conditions, created circumstances that would produce one of the greatest fire disasters in human history. Hamburg had experienced unusually warm and dry weather throughout July. On the night of July 27th, temperatures exceeded 30 degrees Celsius even after dark, unusual for northern Germany. Humidity was only 30%, compared to typical summer values of 40 to 50%. There had been no significant rainfall for over 2 weeks. Wooden, building components, roof timbers, furniture in apartments, all were exceptionally dry and ready to burn. The concentrated bombing created hundreds of separate fires in densely built working-class neighbourhoods of Hammerbrook, Ham, and Borgfelde. Most of Hamburg's fire vehicles had been in western districts, still fighting fires from the earlier raids. Only a few fire units were available in the eastern districts now under attack. Roads blocked by rubble from high-explosive bombs prevented fire services from reaching many burning areas. Under these specific conditions, something unprecedented occurred. The hundreds of separate fires began to merge, creating a self-sustaining thermal convection that pulled in air from surrounding areas with hurricane force. Winds exceeding 150 miles per hour roared through streets toward the fire center, carrying burning debris and spreading flames across entire city blocks. Temperatures in the fire zone exceeded 800 degrees Celsius, hot enough to melt glass and ignite asphalt pavement. This was the phenomenon that would become known as firestorm, though the term itself was not yet in common use. The massive thermal updraft created its own weather system, a tornado of fire 1,500 feet high that consumed everything within a roughly 2-mile circular area. People in air raid shelters suffocated as fires consumed all available oxygen. Those who tried to flee through streets were incinerated by radiant heat or blown into flames by the hurricane-force winds feeding the conflagration. The death toll from this single night would eventually be estimated at between 25,000 and 30,000 people, the majority killed in the firestorm zone. When combined with casualties from other Gomorrah raids, the total Hamburg death toll reached approximately 42,600 civilians killed, 37,000 wounded. Over 1 million people fled the city in the operations. Aftermath. 61% of Hamburg's housing was destroyed or severely damaged. From a purely military strategic perspective, Operation Gomorrah achieved its objectives. Hamburg's shipyards, which had been producing Type 7 and Type 9 U-boats for the Atlantic campaign, suffered severe damage that disrupted production for months. The city's oil refineries sustained heavy damage. Port facilities were rendered inoperative. The psychological impact on German civilian morale was devastating, with interrogation reports from captured personnel revealing widespread belief that Germany could not win a war against enemies capable of such destruction. But the most significant long-term impact was doctrinal rather than tactical. Window had proven that radar-directed defenses could be negated through relatively simple and inexpensive countermeasures. This realization forced fundamental changes in German air defense strategy and accelerated development of backup systems that did not depend solely on radar. German responses to Window evolved through the remainder of 1943 and into 1944, though none fully restored the defensive effectiveness that had existed before Hamburg. The most immediate tactical adaptation was Wild Sow, Wild Boar, a desperate measure conceived by Oberst Harjo Hermann. This technique abandoned radar-guided interceptions entirely, instead relying on visual detection of bombers silhouetted against searchlights, fires, or moonlit clouds. Single-engine day fighters, primarily Me 109 seconds and FTW 190 seconds, were pressed into night service, operating without radar over their own cities during raids. Pilots would fly visual circuits above burning targets, watching for bomber silhouettes against the flames and attacking opportunistically. The tactic achieved some success, but was fundamentally dangerous. German fighters flying visual patterns risked mid-air collisions with each other and friendly fire from anti-aircraft batteries that could not distinguish friend from foe without radar identification systems. 3 specialized Jagdgeschwader, fighter wings designated JG-300, JG-301, and JG-302 were formed specifically for Wild Sow operations. These units achieved notable individual successes, with experienced pilots occasionally shooting down multiple bombers in single sorties. But the overall loss rate among the Wild Boar fighters themselves was unsustainable. Pilots crashed due to poor visibility, mid-air collisions, or simply exhaustion from flying night missions in aircraft not designed for such operations. More sophisticated technical countermeasures progressed slowly. The Würzburg Laus modification, named after the German word for louse, incorporated Doppler filtering to distinguish moving aircraft from stationary or slow-drifting chaff. The system worked by passing radar returns through a bandpass filter that accepted only signals showing frequency shifts between 200 and 700 Hz from the transmitted frequency. Aircraft moving radially toward or away from the radar created such frequency shifts due to Doppler effect. Chaff drifting at wind speed created negligible frequency shift. Laus modifications were ordered for all Würzburg radars between July and August 1943, but implementation proved far slower than planned. Each radar required hardware modifications and operator retraining. Production of the necessary filter components competed with other urgent military electronics demands. By January 1945, approximately 1,000 Laus modification kits had been ordered, but only 40 to 50 were actually operational. The majority of German radar systems remained vulnerable to window throughout the war. The slow pace of technical countermeasure deployment reflected broader problems in German military-industrial organization. Unlike the centralized, efficient Allied production systems, German war production remained fragmented among competing bureaucracies, even late in the war. Radar improvements competed for resources with tank production, jet fighter development, V-weapon programs, and hundreds of other projects, each championed by different military or party officials. Meanwhile, RAF Bomber Command and the American 8th Air Force exploited their window-enabled advantage ruthlessly. Following Hamburg, window became standard equipment on all bomber operations. British factories expanded production to provide millions of bundles monthly. American factories, with their greater manufacturing capacity, eventually produced over 13 million pounds of chaff, supplemented by over 8 million pounds of a longer variant called rope, designed to counter lower-frequency German radar systems. The Americans also developed their own chaff variants tailored to different tactical situations. Standard chaff packets were optimized for the wavelengths of German Würzburg and Freya radars. Specialized rope chaff, consisting of longer aluminum strips, targeted Wassermann and other longer wavelength early warning systems. The diversity of chaff types reflected systematic understanding of the entire German radar network and determination to counter every element. Bomber tactics evolved to maximize window effectiveness. Pathfinder aircraft would seed the approach route with heavy chaff concentrations, creating a radar-opaque corridor through which following bombers could fly. Feint operations, small formations dropping enormous quantities of chaff, created phantom bomber streams that drew night fighters away from actual attack routes. Operation Taxable on the night of June 5th through 6th, 1944, used window-equipped Lancaster bombers circling offshore to simulate a large invasion fleet in the Straits of Dover, deceiving German coastal radar during the actual Normandy landings. The psychological impact on German radar operators and fighter crews was profound. Men who had once possessed technological superiority, who had dominated the night sky through radar-guided precision, found themselves reduced to desperate visual tactics or paralyzed by thousands of false targets. Interrogations of captured Luftwaffe personnel throughout 1944 consistently revealed demoralization stemming from loss of radar effectiveness. One captured night fighter pilot, Lieutenant Wolfgang Schnaufer, who had been an ace with over 30 confirmed kills before his capture, told Allied interrogators in September 1944 that the introduction of window was the moment we knew the night belonged to you, not because we lacked courage or skill, but because our technological advantage had been taken away by strips of paper. Flying visual missions over cities being firestormed by your bombers was suicide. Ground controllers could no longer guide us effectively. We were reduced to hunting in the dark, hoping for lucky visual contacts while you bombed our cities with impunity. Albert Speer, Germany's Minister of Armaments and War Production, later testified at his post-war trial that the Hamburg firestorm, enabled by Window's negation of German radar, made an extraordinary impression on Hitler's closest advisors. Speer recalled telling Hitler that if the Allies conducted 4 or 5 more attacks of Hamburg's scale on other German cities, Germany would be forced to surrender. While this prediction proved overly pessimistic, it reflected the profound psychological shock that window-enabled devastation had created in German leadership. The British paid a price for their window deployment decision. As predicted by those who had argued against its use, Germany immediately began producing its own chaff, called Düppel. German bombers began using Düppel during raids on Britain, though by mid-1943, the Luftwaffe bomber force was so reduced and so consumed by fighting in Russia and the Mediterranean that relatively few raids on Britain were conducted. More significantly, German night fighters began carrying Düppel to confuse Allied radar systems. British night fighters that had been using radar to hunt German aircraft found their own screens clouded by chaff. Ground-controlled interception systems designed to guide RAF night fighters onto German bombers experienced the same degradation that had crippled German systems. The countermeasures race had entered a new phase where both sides possessed similar capabilities and constantly sought new technical advantages. This escalating electronic warfare competition drove rapid innovation on both sides. British scientists developed improved radar systems less susceptible to chaff jamming. The H-2S ground mapping radar used by Pathfinder aircraft operated at higher frequencies and different scanning patterns that made it less vulnerable to window interference. American radar designers developed moving target indication systems that could distinguish aircraft from chaff based on velocity differences. German scientists responded with their own innovations, though handicapped by deteriorating strategic circumstances and resource shortages. The Naxos radar detector allowed German night fighters to home in on emissions from H-2S radars, turning British navigation aids into homing beacons for German interceptors. The Liechtenstein SN-2 airborne intercept radar operated at longer wavelengths than earlier models, making it harder to jam with standard window dimensions, though British designers quickly adapted by producing rope chaff optimized for these new wavelengths. By late 1944, the electromagnetic battle had evolved into extraordinary complexity. Each bomber carried multiple types of chaff tailored to different threat systems. Electronic warfare aircraft equipped with powerful jammers accompanied bomber streams, transmitting noise on known German radar frequencies. German night fighters carried multiple radar detectors to locate different types of Allied transmissions, along with their own jammers to counter British radar systems. The technological competition extended beyond radar and chaff. Infrared detection systems were developed to track aircraft by engine heat rather than radar returns, making them immune to chaff but vulnerable to other countermeasures. Acoustic detection systems attempted to locate bombers by engine noise, though these proved impractical for guiding intercepts due to sound propagation delays and atmospheric distortions. Throughout this escalating competition, one factor remained constant. Window had permanently eliminated the decisive radar advantage that had made German night defences so lethal before July 1943. German fighters and anti-aircraft batteries never regained the kill rates they had achieved in early 1943. Allied bomber losses, while never eliminated entirely, remained far below the unsustainable rates that had threatened the strategic bombing campaign's viability. The statistical evidence was overwhelming. In the 6 months before Window's deployment, January through June 1943, RAF Bomber Command flew approximately 25,000 effective sorties and lost approximately 870 aircraft, a loss rate of 3.5%. In the 6 months after Window deployment, July through December 1943, Bomber Command flew approximately 30,000 effective sorties and lost approximately 840 aircraft, a loss rate of 2.8%. This reduction appears modest, but the implications were enormous. At 3.5% losses, the average crew's survival probability over 30 missions was approximately 35%. At 2.8% losses, survival probability increased to approximately 44%. Nearly 10% more crews would survive to complete their operational tours, representing hundreds of trained airmen who would live rather than die. More critically, The reduced loss rates allowed Bomber Command to expand operations without unsustainable attrition. Monthly sortie rates increased from approximately 4,200 in early 1943 to over 6,000 by early 1944, while absolute monthly losses remained roughly constant. The bombing campaign that had seemed on the verge of collapse in early 1943 became sustainable and continuously escalating in its intensity. American bomber forces, joining the campaign in growing numbers throughout 1943 and 44, benefited equally from Window's effectiveness. Though American daylight raids relied primarily on fighter escorts and tight defensive formations for protection, chaff provided additional degradation of German radar-directed anti-aircraft fire that had been devastatingly accurate against high-altitude formations. The combined bomber offensive reached its peak intensity in early 1945, with thousands of bombers striking German targets daily and nightly. By this point, German air defences had effectively collapsed under the weight of sustained attacks, fuel shortages that grounded fighter aircraft, and the cumulative loss of experienced pilots who could not be replaced. Window had been instrumental in enabling this expansion by reducing losses during the critical period when the campaign might otherwise have become unsustainable. Beyond its immediate tactical impact, Window represented a watershed moment in the evolution of electronic warfare. It demonstrated that relatively simple, low-technology countermeasures could negate sophisticated high-technology systems. This lesson would inform military planning throughout the Cold War and beyond, driving investments in electronic countermeasures that often proved more cost-effective than direct technological competition. The concept of chaff itself became a permanent fixture of military aviation. Modern aircraft, whether fighters, bombers, or helicopters, carry chaff dispensers as standard defensive equipment. Contemporary chaff consists of aluminum-coated glass fibers rather than paper strips, providing better performance and longer persistence in the air, but the fundamental principle remains identical to Joan Curran's 1942 design. Curran herself received far less recognition than her contribution merited. No medals were awarded for her work. No public acknowledgement came during the war years, as Window remained classified. Even in post-war accounts, she was often mentioned only in passing or in the context of her husband Sam Curran's more visible contributions to radar development. R.V. Jones, Britain's wartime scientific intelligence officer, later stated in his memoir Most Secret War that he believed Joan Curran's contribution to Allied victory exceeded that of her husband's, despite Sam's work on the cavity, magnetron. After the war, the Currans moved to the United States to work on the Manhattan Project at Berkeley, California, helping develop the electromagnetic isotope separation process for enriching uranium. There, Joan gave birth to their first child, a daughter named Sheena, who was born severely mentally handicapped. This personal tragedy redirected much of Joan's post-war energy toward advocacy for disabled people's rights and improved care facilities. When Sam Curran returned to Britain to become Professor of Natural Philosophy at Glasgow University and later Principal of the Royal College of Science and Technology, Joan established the Scottish Society for the Parents of Mentally Handicapped Children in 1954. This organisation eventually grew to over 100 branches and 5,000 members, transforming support services for disabled individuals across Scotland. Joan Curran was eventually awarded an honorary Doctor of Letters from the University of Tymerais bin Dargis, Strathclyde, in 1987, recognition that came 4 decades after her war work and shortly before her death in 1999. Her obituaries mentioned Window, but even then failed to fully capture how dramatically her kitchen table experiments with household scissors and aluminum foil had altered the course of the air war. The paradox of Window's impact lies in its simplicity. In a war characterized by increasingly complex technology, from radar to jet engines to atomic weapons, one of the most decisive innovations was strips of aluminum-coated paper. The sophistication lay not in the technology itself, but in understanding the electromagnetic principles that made simple metallic strips so effective against complex radar systems. This understanding required deep knowledge of wave propagation, resonant frequencies, and radar signal processing. It required systematic experimentation to determine optimal strip dimensions, dispersal patterns, and deployment techniques. It required production expertise to manufacture millions of strips with consistent quality. Most critically, it required the strategic courage to deploy a countermeasure that enemies could easily copy, risking retaliation for the sake of immediate tactical advantage. Joan Curran possessed the scientific understanding to design window effectively. British industry possessed the manufacturing capacity to produce it in war-winning quantities. RAF Bomber Command possessed the operational need that finally overcame bureaucratic resistance to deployment. The conjunction of these three factors, at precisely the moment when German air defences threatened to make strategic bombing impossible, transformed the European air war. On that February morning in 1942, cutting aluminum foil at her kitchen table, Joan Curran could not have predicted the full scope of what she was creating. She understood the electromagnetic principles. She had calculated the optimal dimensions. She had envisioned the clouds of drifting reflectors, confusing German radar displays. But she could not have foreseen the firestorm at Hamburg, the million refugees fleeing that burning city, the Allied bombers that would survive to drop their ordnance and return home to fly again. She could not have foreseen that her household scissors would effectively triple bomber crew survival rates, enabling the strategic bombing campaign that would help destroy Nazi Germany's ability to wage war. She could not have predicted that her simple invention would remain relevant 80 years later, carried aboard every military aircraft in the world as standard defensive equipment. She could not have known that historians would later rank window, alongside radar itself, as one of the most consequential technologies of the Second World War. The story of window is ultimately a story about the intersection of scientific understanding, industrial capability, and strategic necessity. It demonstrates that wars are won not merely through courage or numbers, but through systematic application of knowledge to military problems. It shows that simple solutions, if based on sound physical principles, can defeat complex systems. Most fundamentally, it reveals how individual scientific contributions, often unrecognized and uncelebrated, can alter the course of history. When Obergefreiter Hans Richter watched his Würzburg radar screen turn white with phantom returns at 23 minutes past midnight on July 25, 1943, he was witnessing the end of German radar supremacy in the night skies over Europe. When Flying Officer James Morton watched searchlights wander aimlessly across the Hamburg sky instead of focusing on his bomber formation, he was experiencing the first fruits of Joan Curran's genius. Neither man knew the other's name. Neither understood the full technological and tactical revolution occurring around them, but both were participants in a transformation of aerial warfare as profound as any that occurred during the Second World War. The electromagnetic dimension of battle had been opened, exploited, and decisively turned against those who had once dominated it. The bundles of aluminum-coated paper strips, each weighing 1 pound, each containing approximately 2,000 precisely cut pieces, measuring 25 centimeters by 1 to 2 centimeters, had accomplished what years of tactical innovation and technological development could not. They had made the invisible visible on German radar screens while simultaneously making the visible, the actual British bombers, invisible among thousands of phantom returns. In the end, the history of window validates a principle that extends far beyond radar or aerial warfare, that understanding the fundamental physics of a problem can lead to elegant solutions that sophisticated engineering alone might never discover. Joan Curran understood that radar detected electromagnetic reflections from conductive surfaces. She understood that surfaces of specific dimensions could generate strong reflections at specific frequencies. From these simple physical principles, she extrapolated a countermeasure that changed the war. The mathematical certainty of this approach contrasted sharply with the statistical uncertainty that had characterized RAF Bomber Command's operations before window. Before July 1943, bomber crews calculated death probabilities before each mission, watching those probabilities accumulate towards statistical certainty of being shot down. After window, those same crews watched searchlights grope blindly through the sky and flak burst harmlessly at incorrect altitudes, physical evidence that the enemy could no longer see them clearly. That transformation, from resignation to death toward reasonable hope of survival, represented Window's greatest achievement. It was measured not in tons of bombs dropped or cities destroyed, but in young men who lived to see their families again, in crews who completed their operational tours and went home, in the psychological shift from fatalism to confidence that permeated RAF Bomber Command after Hamburg proved Window's effectiveness. 21 months after Hamburg, on May 8, 1945, Germany surrendered unconditionally. The strategic bombing campaign, enabled in part by Window's negation of German radar defences, had contributed substantially to that surrender by destroying Germany's industrial capacity, disrupting transportation networks, and forcing reallocation of resources to air defence that might otherwise have supported frontline combat operations. Historians debate the precise contribution of strategic bombing to Allied victory, with arguments ranging from those who consider it decisive to those who view it as marginally effective relative to its enormous cost. But one aspect remains indisputable. Without Window, the bombing, a campaign as actually conducted, would have been impossible. Loss rates in early 1943 were trending toward levels that would have forced suspension or radical redesign of strategic bombing operations. Joan Curran's aluminum strips, manufactured by the millions in British factories and dropped by the ton from Allied bombers, enabled the campaign to continue and expand precisely when it faced potential collapse. That contribution, however one assesses strategic bombing's overall effectiveness, was undeniably significant to the war's prosecution and outcome. The examination of chaff bundles by German scientists in the wreckage-strewn streets of Hamburg on July 25, 1943 had been an autopsy, not a diagnosis. By the time German engineers understood what Allied technology had achieved, the strategic outcome was already determined. The mathematics were irrefutable, the physics unforgiving, the tactical implications inescapable. They returned from Hamburg to their research stations and headquarters, carrying knowledge that their finest radar systems could be blinded by paper and aluminum foil, that their integrated air defense network could be overwhelmed by clouds of drifting reflectors that cost pennies to produce. They fought on because duty demanded it, and hope dies slowly. But they knew the examination of those crumpled metallic strips had shown them the future, and in that future, the night sky belonged to the Allies. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.